All right. Good morning and happy Friday. It's already end of week 2. All right. Let's take a look at our lecture for today. And the topic is regularization. So on Monday we looked at cross-validation as a way to kind of pick which model is the best, quote, best model, or the model that's going to make good predictions. And, one of the reasons why we do cross-validation is because we want to avoid this problem of overfitting, okay? And so, in overfitting, that's the idea that you end up, as part of your model, you're including like weird little details that exist in your training data, but don't actually, generalize to the population, right? So you have like, some kind of weird thing is happening in your training data, but it's just kind of like a coincidence there. And so, what cross-validation does is it kind of chops up your training data into little different parts, so you don't end up overfitting kind of the entire data set. You're working with kind of a subset, so you're a little bit less likely to overfit, and so anyway, that's one of the tools, right? It says a model's performance there is not based on how it performs on just fitting the data that was used to train, but it's measured by looking at data that wasn't used as part of the training process. Another method that helps us avoid overfitting is this idea of regularization, okay? And what regularization does is it modifies the loss function that we're using. Traditionally, we've been using mean squared error or sum of squared errors, and we're going to kind of change the way we measure loss by including a term that penalizes complex models, okay? So this is our loss function. Mean squared error, or if you get rid of the 1 over n term, it's going to be total sum of squared errors. And with this definition, our definition of best is the model that minimizes this mean squared error. Okay, and if we say our only objective and our only goal is to minimize the mean squared error, then what's going to end up happening is we end up picking an overly complicated model. We end up picking a model that we're trying to get the highest r squared, or we're trying to get the minimum mean squared error, and so we might pick the one with 17 terms, okay, because that one is going to really shrink your mean squared error, right? And we avoided picking the one with 17 terms by doing cross-validation, or you have other kind of tools to avoid this, but we're going to look at using regularization as a way to try to avoid using the one with 17 terms, okay? In your homework assignment, I think one of the assignments was, okay, instead of using mean squared error, what if you use this weighted least squares, okay? And so that's an example of modifying the loss function. And so when you use weighted least squares, you're saying, some of these, some of the residuals are like more important than others, right? It's more important that we minimize this residual than that residual, right? You apply a heavier weight on certain residuals, and so that what ends up happening is you end up picking different parameters that you normally would if you used just mean squared error. So if you used just the regular thing, you would pick a certain slope and intercept, but for like weighted least squares, you'd end up picking a different slope and intercept because you're trying to minimize that modified function. And so similarly, what we're going to look at today is, okay, well, we will modify the loss function, but we're going to do it in a different way. And this is how we're going to modify our loss function. We're going to say, let's take this L right here. The loss function here is the mean squared error, okay? Mean squared error right here. And we're going to add basically a complexity term, okay? And so when you have the ordinary least squares loss function plus the complexity term, that's what we will call our regularized loss function, okay? So all it is we're just saying, okay, we want to minimize this thing, but we're also going to tack on something else, and we want to minimize the combination of the two, okay? I guess, you could think of it as, the total that you have to pay for something is kind of like the cost plus shipping, right? And, you go online and you search at different places and you go, oh, okay, you know what? This place sells the product, but then this place, these different stores sell the product. This place, if I order over here, I don't have to, shipping is zero. If I go over here, maybe the cost of the product itself is lower, but I have to pay more for shipping or something like that, right? So the total that you're going in is going to be, the total of these two things together. So here, it's not just the cost by itself, but there's also this kind of penalty, right? And so you can say, oh, sure, I can get it cheaper if I order internationally, but now I have to pay more shipping, right? So now it's like, oh yeah, I can get better, reduce my ordinary least squares error, my mean squared error, but now I have to pay extra for the 17 terms that I'm using. And we say, okay, well, maybe I don't want to pay extra for the 17 terms, and so I want maybe I'm okay with having a slightly higher OLS if I only have 3 terms or something, right? The complexity there is less. So this is kind of the idea is, now we have this kind of the thing we're minimizing is a combination of our mean squared error plus this other thing for complexity, okay? And so what's going to end up happening is the slope and your intercept and your other kind of weights and coefficients will be, a little bit different from the OLS coefficients. Okay, so here's another kind of analogy that I use is like, you're searching for an apartment, okay? I don't know how much an apartment costs, right? There's different, right? If you had to pay for an apartment by yourself or something, one place might cost $2,400 a month, and your commute is 10 minutes, okay? And another apartment might cost less per month in rent, but your commute is much higher, right? And you have to kind of make choices about what's more important, right? So here it's a little bit harder to assess because it's not just money. It's not like cost plus money plus money. It's right. You got this money, and then you have this other kind of this amorphous thing. Over here it was complexity. Okay, over here it's like time, right? And so if money were the only thing that mattered, you just pick the apartment that's the cheapest. That's easy. Okay, but most people value their time to some degree, right? And so you say, well, okay, I could save money, but now I have to spend more time commuting. And now you have to kind of ask yourself, well, how much is my time worth, right? And so if, your time is like super valuable to you, or maybe you just really hate commuting, then you'd say, okay, this higher penalty, that's no good, right? So you'll probably select the apartment that's closer to work, and you'll say, I'm willing to pay this much extra per month in order to save this much time per month in order to avoid driving and all of that stuff. Or, on the other hand, if you're like, you know what, I don't mind sitting in traffic, like it's not so bad. I can like listen to a podcast or whatever, and it's kind of nice to just have this break from the world or something, right? You'd be like, okay, I actually enjoy having a commute or something, right? And then you'd say, yeah, you know what? Save some money, have some peace and quiet, during that car ride. Everybody's different, right? Some people like the idea of sitting in traffic is miserable, and others, I actually don't. I don't want a super long commute, but the drive I don't mind. Okay, So, the true cost, however we're going to measure it, is going to be, the rent money plus some kind of, conversion factor or preference factor times like the commute, right? And the conversion factor will be like how much, dollars per minute type of thing. Okay, so that's kind of, we're doing something similar, okay? A little bit different. Oh, I forgot this. The projection always cuts this off. Unlike kind of this apartment selection, we're not looking at like one apartment versus another apartment or something, or one model versus another model. What we've done is we've modified the loss function. And so with that in mind, we're going to kind of go through and say, what is the model? What is the slope and intercept and, whatever weight terms that's going to end up minimizing this total loss, this regularized loss, this loss that includes not just the mean squared error, but also this penalty term for how complex our model is. Okay. So what it looks like, again, is we have this, I just said the regularized loss is, our OLS loss plus this complexity parameter, all right? And so more generally, so here I just wrote complexity, but we we express complexity using this function, R of F, F being kind of our model, and R of F being this kind of complexity penalty, okay? And, how do you do this? Well, there's some stuff that you can read on regularized least squares, and it kind of talks about some of these things here. Here I'm using and one thing to note, this L prime, I'm following the textbook notation, and I recognize that this can be a little bit confusing because a lot of times prime is associated with derivatives, but this is not the derivative of the loss function, okay? This is L prime indicating it's a function related to the loss function, but not the loss function, okay? So, math notation, it's like every textbook you pick up, slightly different, and, we've got similar concepts, but it's, so not the derivative of the loss function, it's the regularized loss function, something related to L, but not exactly the same, and that's what this is, okay? All right, so let's, how do we measure a model's complexity? And so there's a few ideas, and so let's just keep it simple. Let's say we're comparing model A with model B. Model A fits a fourth order polynomial. Model B fits a fifth order polynomial. And, based on that, we can say, oh yeah, the fifth order polynomial more complicated than the fourth order polynomial, okay? And so, I think I got these letters mixed up, but we'll say, okay, if you have the fifth order polynomial, you have basically 6 weight terms. You have an intercept and weight terms 1, 2, 3, 4, 5 for each of your kind of components, right? Your W1, W2, W3, W4, W5. And then, if we say, oh, you know what, the fifth W5, if we say W5 equals 0, then now it's a fourth order polynomial, okay? So, one way to measure model complexity is you just say, well, how many coefficients are non-zero, okay? And we just say, okay, well, how many of these W terms are not 0? And more W terms that are not 0, more complicated model. Fewer W terms that are non-zero is a simpler model, okay? So this one has 5 W terms that aren't 0. This one has 6 W terms, and we'll say, okay, 5 terms means less complicated, 6 terms means more complicated, okay? The idea of how many are non-zero can also be thought of as the L0 norm, basically just how many things are not 0. That's the L0 norm of a vector. And so that's one way for us to measure it, right? So we can say, take our vector W, our vector of weights, and we can say, all right, what's the L0 norm of the vector? And that's basically how many terms are not zero, okay? One problem is that this thing is very difficult to optimize, okay? Because it's kind of like this, I don't know, it gets messy, right? And you technically have to consider all the different possible permutations and of which the elements in W are non-zero. So, right, it's not necessarily that, the higher order terms have to be zero and you kind of build them up incrementally, but it could be like, oh, the second term is zero and the third term is not zero and the fourth term is zero or something. And so a whole bunch of different permutations. It gets real messy, real complicated, right? Basically 2 to the length of W, different kind of combinations. And then not only just the different combinations, but like what are the different actual W's that you should use, okay? And so it gets real messy, okay? So we generally don't bother trying to solve this thing. Okay? We say, all right, this one's too hard. Let's find an easier function to work with. Okay. All right. Wait. Let me give you your first view quiz answer, which is week 2 Friday. First view quiz answer is D. D as in dog. D. D is our first view quiz answer. So we're not going to bother with this thing, right? A lot of these things that we do in machine learning is we go, oh, that's a cool idea, but it's also way too hard. So on a practical level, we're not gonna go for it, right? Okay, so we say, all right, well, instead of the L0 norm, what if we use the L1 norm? Okay, so the L1 norm of a vector is the sum of the absolute values of the vector. Okay, so you take each term in your vector, you take the absolute value of it, and you sum them up. That's your L1 norm. It's like the Manhattan norm. Basically, you're just taking all of the distances of these things, and exactly the whatever, the length this way and the length this way, and you just add them up, type of thing. Okay, and that can serve as a measure of the complexity of the model. Now, so basically, if you have a non-zero value of W, that's going to contribute to the penalty factor, and larger values of W contribute more to the penalty, and a coefficient is 0. If one of the W's is 0, then that variable basically does not contribute to the penalty factor, and it kind of makes sense because if your coefficient's 0, that's not really a term in your model, okay? And so, if this is your loss function, your regularized loss function, when you're trying to optimize and you're trying to pick your W's, if you think about, what happens to your OLS function, okay, you can say, all right, if I include this third parameter or this fourth parameter, this additional parameter, I can shrink my ordinary least squares loss, my mean squared error, by a little bit, right? Including another term, I can shrink this thing. But then, by including that term, now my penalties starts to go up too. So however much this is shrinking by including additional term has to be more than however much my penalty is going up, right? Because there's kind of two things going up, right? Like I can save a little bit on the price, but now my shipping goes up, and so how much you save this side has to be more than how much it goes up over here. And see, that kind of goes in there. When we use the L1 norm, this thing is called the lasso. I forget what lasso stands for. Least absolute shrinkage and selection operator. Okay. That's what it stands for, lasso. And here it says minimize. So what we're seeing here, this is just, this is more, okay, this is minimizing your OLS, and here it introduces it as a constraint, okay, that the sum of the terms is less than t. That's another way to think of it. Is you can say, so you can say, minimize this subject to a constraint, or what we are seeing is this is your OLS part over here plus this, and this is kind of minimizing. Minimizing a function subject to a constraint. You can do that using a Lagrange multiplier, and basically you add in the Lagrange term over here, and that's basically what we're doing here, right? So different notation on Wikipedia, right? So anytime you go, oh, I want to learn a little bit more, and I go on Wikipedia, you got to be like, oh, Wikipedia uses betas and stuff, which is probably a little bit more common, but our textbook uses W's, which is fine, but that's what goes, okay? And then the other thing that we might use is the L2 norm, okay? Or the L2 norm squared, right? So this one is you're looking at the squared values of the elements in W, okay? So, so not the Manhattan norm, but like now you're kind of Euclidean distance thing, or I guess squared Euclidean distance, all right? So you take the elements in W, you square them, you add them all up, okay? And what that does is when you square these things, larger values of W are penalized more heavily than smaller values of W, okay? And values of W that are less than 1, their penalty is even smaller, right? Because if you square something less than 1, it gets even smaller, type of thing. And this thing is known as ridge regression, okay? One effect of ridge regression is that it ends up just kind of preferring when a bunch of the W's are smaller and similar in size. Okay, so these are different ways for us to kind of consider penalty factors for complexity. One objection that you might have is, how does the size of the coefficient, the W, like why does that matter as far as the complexity goes, right? Because if you say, well, how many W's are not 0, that kind of makes sense. You go, okay, 6 terms are not 0, that's more terms. Okay, over here, 5 terms aren't 0, that's fewer terms. So I get, I can understand why having more terms means a more complicated model, okay? But why would, 2 models that both have 6 terms and this model happens to have bigger terms, why is that one like the more complicated model, right? Because if you look at this, right, if you look at something like this or like this, you can have 2 models with the same number of terms, but the one with larger W's is going to get penalized more for complexity. And so you might wonder, like, why should the size of the W factor in, right? If 2 models have the same number of variables, aren't they equally complex? And why would one model be more complicated if it just simply because it has a bigger coefficient? And then another kind of problem with this is, okay, if bigger coefficients means more complexity, what if I just changed the units, right? If I changed the units, then that's going to change the size of the coefficient, and I can like artificially shrink my weights by changing the units, right? So instead of measuring in feet, I can measure in centimeters or something, and now my coefficients are going to, grow or shrink or something like that. Okay. And yeah, that's true too. So I'm going to try to address these concerns. Okay. So one thing about the changing of units, that's usually addressed by standardizing your input variables. Okay. So basically, you will kind of like standardize them. You'll subtract off the mean, divide by the standard deviation, and so you'll often, center your vector so that it has mean 0, and then you standardize them, divide by the size of your standard deviation so that the resulting values have a standard deviation of 1. So basically you're turning everything into z-scores, and if you turn everything into z-scores, then then you don't have to worry about the units, right? Because if you change the units, your z-scores will still remain the same, okay? Or, if you can't have negative numbers, for, whatever reason you're dealing with like log values or something, then another value is to kind of just like scale them so they all go from 0 to 1 type of thing. So that's another way to, standardize your variables, okay? And so, standardizing variables addresses the current concern using different units, okay? So that's going to be recommended anytime you see a recommendation to use lasso or ridge regression. You should probably standardize your variables first. Okay. Yeah. Well, I guess not always. Sometimes there's different cases where it's like, oh, you know what, we want to leave the variables as is, but that's often what we want to do. Okay. All right. What about this other idea of just like, okay, so why would two models with the same number of terms, but one having more, larger coefficient, why is that one more complicated? Okay. So let's just kind of think about this for a second. Okay. So let's say we have two competing models for the same input matrix X. Okay. X has been centered and standardized. And both models have 4 X variables. And both models have the same coefficients for X1, X2, and X3. So we'll have W1, W2, W3. Those are the same. But then model A will say the weight for the 4th X variable, X4, is 1. And model B has the weight there to be 0.01. Okay? And I'm going to try to argue that model B is less complicated than model A, okay, because it has a smaller coefficient, all right? So other than this coefficient for W4, model A and model B are the same, and I'm going to argue that model B is less complicated because its W4 coefficient is smaller, okay? When you have a tiny coefficient for a variable, changes in that predictor variable basically has less impact on the outcome variable, right? So if model B has a tiny coefficient for X4, it's basically placing less importance on X4, considering the variables have been centered and standardized. What model B is saying is that, if X4 goes up 10 points, I'm only going to adjust it by 0.1, all right? Versus model A, if X4 goes up 10 points, then we have to adjust our prediction by 10 points as well, okay? So even though model A and model B both use variable X4 as part of refining its prediction, model B is much closer to just ignoring the X4 variable altogether. And I argue that because it's closer to just ignoring it, it's the simpler model, okay? Another analogy is let's say we've got two different students and both of them are involved in several clubs on campus. But one of these students is like fully invested in all of their clubs. So they're like, they're officer positions on like multiple clubs. And you can say like, oh man, you're really busy, right? Because it's like anytime their club has an event or something, they have to organize and plan and whatever, okay? The other student is also involved in the same number of clubs, but, this other student is not as active and invested and, kind of just has the attitude of like, yeah, maybe I'll go to the event, maybe I won't, okay? So both students, same number of clubs, I would argue the one that's less invested has a simpler life than the one that's fully invested in all of these things, okay? And it's kind of like that for these models, right? The one that has a bigger coefficient on all of these terms, I would say, is a more complicated model because it's like weighting all of these different terms, heavier than the one that has, smaller coefficients, okay? So we can use the size of the coefficients as a way to kind of measure how complex the model is. Not just how many terms we have, but also just the size of the coefficient itself. All right, I don't know, I hope that works as kind of an argument for why we're using the size and not just the number of terms. Okay. Okay. So one note: when calculating the lasso or ridge penalty based on the model coefficients, don't include the intercept term. Only coefficients multiplied with the predictor variables are included in the penalty term. So you wouldn't use the intercept as part of the penalty. Okay. So let's try out a simple example here. Okay, I've got x1 and x2, and these are just 1, 2, 3, 4, 1, 2, 3, 4, and so on and so forth. And we're going to say the true target value is going to be 1.5 x1 plus 0.5 x2. Okay, and these two things are on the same scale. I'm not going to bother centering and scaling them. I'm going to add some noise. Okay, I'm going to just add some random normal noise to the true values of t, and so these will be my observed t values. Okay, so I've got observed values, which is centered around the true values here. Okay, and my OLS model. Okay, I can estimate coefficients by fitting a linear model to by predicting t based on x1 and x2, and I'm not going to bother fitting an intercept in this thing. Okay, and so based on that, my coefficients with the data I have, I estimate the coefficient for x1 to be 1.458 and the coefficient for x2 to be 0.453. Okay, and the true values are 1.5 and 0.5. So we get something kind of close, but not exactly that, and that makes sense because these subject to random noise. Okay, let me give you your second view quiz answer, which is the letter A. A as in apple. A is your second view quiz answer. Okay, all right. So here I can do I can use my loss function. I can create a loss function, and I don't know. Did you guys learn how to use optim, the function optim? So I covered this in my 102A class. If you didn't take 102A with me, you may or may not have covered how to use optim. But with optim, you write basically a function in R, and you tell R, I want to optimize this function. So here the function I've written is called OLS underscore OP for optim. Okay, and basically what I'm trying to do is I'm trying to minimize this thing. Okay, and the OLS, this is just a wrapper function, so that when I plug in the parameters, it's going to come out and spit out some value. And basically the parameters will take in my intercept and, or not intercept and slope, my W1 and W2 coefficients, all right, and they gather them together in a W matrix, and I just do T minus X W transpose times T minus X W, and it's going to return that, and that's going to give us a single value. And I'm just trying to minimize this quantity here. And it says and so R can optimize this, and it says, okay, the values of W1 and W2 that minimize, T minus XW transpose and times T minus XW is 1.458 and 0.4533, okay? Which matches pretty much what we have here. Okay, it's not, the optim functions are iterative, and so they don't go for an analytic solution, they go for an approximate solution, which means their final answers will often be close to, but not exactly the same. And so if you look at these numbers and the true numbers that minimize according to LM, they're close, but not exactly the same. But we're pretty much getting the W1 and W2 coefficients, okay? And I'm used to saying intercept and slope, but they're not intercept and slope. They're the coefficient for W1, X1 and the coefficient for X2, W1 and W2 coefficients. Okay. I can plot the contours of the loss function, and right now this is just the OLS loss function, and it's this, what do we call this shape? A paraboloid, okay? It's just kind of like, this bowl shape, where the bowl is kind of like these ellipses, and this is your W1 coefficient, and this is your W2 coefficient, and we can see this red dot. Okay, this is at the minimum of the OLS function, and that's right around 1.5.5. It's if we plotted it, it would be at a 1.458 and 0.4533. So if you were to find this coordinate, this would be 1.458, 0.4533. So this is the value of W1 and W2 that would minimize the OLS. And as we deviate from this, we can see the loss function gets bigger and bigger and bigger. Okay. What happens when we do the L1 penalty? Okay, so when we apply the lasso, here I'm going to just write that as a function in R. All right, I'm going to say the L1 loss is a function, and here I plug in the OLS loss. The OLS loss is this function that I've written back here, which just does T minus XW transpose times T minus XW, plus, and here I'm doing lambda times the sum of the absolute values of W1 and W2. So here I'm just writing a function that's going to calculate this. I calculate the OLS loss plus lambda times my W1 and W2 coefficients. Okay. And so, I'm going to plug this into Optim. So I create a wrapper function, and I just say, all right, you know what? We're going to be able to change our lambda values, and we're going to calculate the loss function. Here's a diagram that I took from a different textbook. Okay. One thing is, if we cared only about minimizing the L1 norm, okay, which is kind of silly. But if I basically weighted the lambda to be a huge number, so that the OLS function, basically is tiny in comparison to this, and we're really only focusing on minimizing the L1 norm, then what would the contours of the loss function look like? They would look like these diamonds, because this is as W1 gets bigger. If W2 were 0, okay, we're just trying to minimize the absolute value of W1, and then if W1 were 0, we would just be trying to minimize the W2. And if you think about the absolute value of W1 and W2, this solid line here, this diagonal line, is kind of like all of the places where W1 and the sum of W1 and W2 are the same, right? So if you're looking at where does W1 and W2 add up to 2, you can have 0, 2, 0.5, 1.5, 1, 1, 1.5, 0.5, 2, 0, right? And you get a diagonal line, okay? Similarly, you can do like 0, negative 2, and what is this, 0.5, negative 1.5, and so on and so forth, right? So you get these diagonal lines, these diamonds that indicate, are areas where the sum of W1 and W2 add up to the same value. Okay, and so if we were only focused on minimizing the L1 norm, these are what the contours would look like, and the value that kind of, when we're trying to minimize, we're often going to end up at like one of these corners type of thing, okay? But here we're not minimizing just the L1 norm, but we're minimizing a combination of the L1 norm and the OLS loss. And so we're going to get something in between, kind of minimizing the OLS function and minimizing these diamonds, okay? And so so we can see what's going to happen. And so let me just show you what happens when I use different lambda terms, right? So these are the functions that minimize the OLS function, okay? 1.458 and 0.453. And if I increase lambda, these terms shrink a little bit, from 1.458 to 1.436 to 1.345 to 1.231. And the x2 terms shrink from 0.453 to 0.430 to 0.339 to 0.225. and they keep shrinking. And if I have lambda equal to, say, 500, both of these things have shrunk down to basically 0. Okay. This is a plot of the contour function where I now have include the lambda thing. All right, and so this kind of looks the same as OLS, but if you look, and what I've done, these blue lines indicate 0, 0. This is where, this blue line would be where W2 is equal to 0, and this blue line indicates where W1 is equal to 0. And right now, everything looks kind of smooth, but as I increase my lambda, you'll see, oh, you know what, we get these kind of this funny little bends right at the where W, one of the W's turned into 0. Okay, and basically what's happening is we are kind of, it's like we're like having a morph between this contour plot where you got a bunch of diamonds and this contour plot where you have a bunch of ellipses. Okay, and so as I increase my lambda, you're going to get like a morph between the ellipses and those diamonds. All right, and so as I increase my lambda, the shape gets kind of more and more like the diamonds. Okay, and what we see is, and this blue dot here is the resulting W1 and W2 that minimize the regularized loss function. Okay, so red dot is the value of W1 and W2 that minimize the ordinary least squares regression. Okay, that minimize the sum of the squared loss. And the blue dot is the value that minimizes the loss plus the complexity parameter. Okay, the regularized loss. And what we see is that as I increase lambda, it pulls the dot diagonally towards this line here. And then when it hits this line, it's not going to keep going because now we've achieved the minimum possible penalty with respect to W2, right? Like I can't shrink W2 anymore to minimize my penalty. So now all that's left is shrinking the W1, okay? So in the beginning, I shrink W1 and W2 kind of equally, right? The penalty gets applied to W1 and W2 both, and so it's traveling in this diagonal line. And then once I shrink W2 to 0, I can't shrink it anymore, and so now I just shrink W1, and we can see it, continuing to 0. And until I've penalized both of these terms so much that it just says, oh, you know what? Let's just go with 0, 0. Okay, and this is how we're going to minimize the thing. Okay. All right, so that's what happens there. And so I've written kind of my observations there. Let me give you your last view quiz answer, which is the letter E. E as in elephant. E as in elephant. Okay, and so we see, the optimal parameter values travel diagonally until it hits one of the axes, and then they get kind of pulled to 0. With the L2 penalty function, okay, we are minimizing. Oh, I'm sorry. I left off a little 2 here. There needs to be a tiny little norm 2 squared. Okay, sum of squared W's. So we're gonna do that. I've got some of the W1, W2 squared things there. Okay, and then so what we see is as I increase lambda, okay, as lambda gets bigger, this term 1.45 goes from 1.45 to 1.24 to 0.92 to 0.74. Interestingly, the x2 value goes from 0.45 to something bigger, to 0.579 to 0.635. Now starting to shrink, 0.573. Okay, and then I keep increasing my lambdas, and both of these shrink further, but they get to something like 0.31 and 0.272. Okay, what's going on here? Okay, all right. So the contours of the OLS are these ellipses. What are the contours of W1 squared plus W2 squared? Circles, right? W1 squared, x1 squared plus x2 squared, or W1 squared and W2 squared, those would be circles. And so on one end, you've got these ellipses. The other end, you've got these circles, concentric circles around the origin. And again, you're kind of having this morph between the two, okay? And so, here on this end, we're starting off at circles, and what we're going to see is we're going to see these contour lines kind of morph. We start off with these ellipses, and what we're going to see is that these shapes start to morph towards the circles, okay? And this is what happens here, okay? As I increase the lambdas, we get more towards circles around the origin. As I go backwards, we get something closer to the ellipses for OLS. I have this diagonal line at W1 equals W2. And then what that indicates is, where the coefficients W1 and W2 are equal to each other, right? Because that's where, you get the circle. And what we see is that, because we're squaring the coefficient, the larger coefficient gets penalized heavier, the smaller coefficient gets penalized less. And so as I increase my lambda, okay, it actually it says, you know what, we're going to get improvement by shrinking W1, okay? And we actually, because we kind of shrank W1, we can kind of offset the, our OLS actually suffers a little bit when I shrink my W1. And I can actually kind of offset that a little bit by kind of increasing my W2, okay? And so we actually increase our W2, and it, our penalty doesn't get too bad, right? And so what we see is that this, the optimal parameters actually get drawn closer to this kind of W1 equal to W2 first. So if I trace the path of that thing, we can see it kind of start approaching that line W1, W2. And then now it says, okay, now if I want to improve kind of the regularized loss, now I have to kind of shrink both of those things together. And so that's what we kind of see here. So it's kind of following this, starts getting drawn to this thing, and then it gets drawn towards the origin here, okay? And even with lambda equal to 1,000, we never actually get 0, 0, because as the coefficients shrink, when you square them, they get even smaller. So, and so this is just a slide that talks a little bit about this. So, when you have big terms and you're squaring the loss, it's going to shrink those more. Okay, so going from shrinking 11 down to 10, the loss shrinks from 121 down to 100. Right, you're shrinking your loss by like 21 points. Versus shrinking from 3 to 2 goes from 9 to 4, and you're only shrinking by like 5 points. So it prioritizes shrinking the big coefficients over the smaller ones. Okay, and certainly when they're even like less than 1, then the amount that shrinks is even smaller. Okay. Another way to think about this is we can think of minimizing. So I've been kind of showing the contours as like a hybrid between the OLS and these either circles or these diamonds. Okay. Another way to think about lasso and ridge is you can think of them as minimizing the RSS or your OLS loss term subject to a constraint, right? Using a Lagrange multiplier. So if you think about, how do we minimize a function subject to a constraint, we can use, a Lagrange term. And basically what you do is you take the function that you want to minimize and you add, lambda times that constraint. Okay. And so for ridge regression, the constraint is basically the sum of your beta squared terms, or your W terms squared, okay? And over here for lasso, your constraint is that the absolute values, the sum of your absolute values is equal to some term, right? Here, I'm using the betas or something. This is kind of the Wikipedia notation, I guess. And so this is kind of the diagram. We're trying to minimize our OLS losses, our OLS function subject to the constraint. Here for lasso, the constraints are the absolute values of beta 1 and beta 2 have to be less than some value. And for ridge regression, the constraint is that the sum of the betas, or your sum of your w's squared, have to be less than some term there. Okay, so you can also think of it that way. Right? And so we can see, with lasso, because of the constraints are these diamond shapes, you're going to end up kind of getting values over here. Okay, I'm going to run out of time here. Here I've plotted I just want to show you what happens here. This cloud of points, and I'm sorry for going over. The cloud of points here represents, if I change the random noise in the very beginning, you might get a W1 that's a little bit bigger, a W2 that's a little bit bigger, a little bit smaller. And so if I change the amount of random noise, these are all of the kind of the different cloud of points that I can get for W1 and W2, right? So there's variance in my W1 and W2 estimates based on the random noise that gets added in, okay? And they're all centered around the true value of 1.5.5, but again, because of random noise, we might get something higher or lower, right? So this is the idea of variance in your estimate terms. When I do lasso, what happens is these are, if I include a lasso, basically what happens is my estimates, they just get shifted a little bit, okay? And as lasso gets bigger, my cloud of points just kind of shift in this diagonal fashion. What happens though is when the cloud of points hits the one of the axes, they all just stays stuck at 0, okay? And so so by kind of, having kind of this limit where, the W's can't become negative or something, okay, we are reducing the amount of variance, okay? And so this is showing like what happens, and here all of the terms just became 0 when I had, a large enough penalty, okay? And so this reduces the amount of variance by in that way, okay? Over here, if I use ridge regression, what happens is as I increase my lambdas, okay, what happens is even with the different kind of random noise, the cloud of estimates just becomes, kind of this much more compact thing. So we reduce the amount of kind of variance we can get with our W1 and W2 estimates there. Okay, so a little bit there. All right, sorry, going over time here. So we'll go ahead. Wait, I need to give you your third view quiz answer? No, I already gave it to you. Okay, all right, so we will go ahead and end. Have a great weekend. We'll see you next week.